is a series of several different types of acid being titrated by strong base. And so you can see here it starts with strong acid, and that gives us our typical strong acid curve where there's enough of that strong acid present that adding hydroxide really doesn't do much to it at all until all of a sudden that strong acid has been titrated away. But now here we can see if we add various weak acids corresponding to these Ka values. And so you can see here that those are getting weaker and weaker as you go up. And what's apparent there is the weaker the acid is as you start, the higher its starting pH is, but also the more prominent this buffering effect. This is what I like to call a shoulder because it looks like a shoulder, right? We're pretty basic the way we describe things in chemistry. So that shoulder becomes much more prominent because as these acids get weaker and weaker, they don't have as much of this buffering capacity, this ability to resist that pH change. So there's another interesting relationship that we can see here. So by this question, and I'm going to put down the Henderson-Hasselbalch equation as a means of seeing if there's something special going on here. Okay, so we remember this is the Henderson-Hasselbalch equation, pH equals pKa plus the log of A minus over HA. And so you notice here that it's for all of these acids in this example, they're all hitting their equivalence point at 50 milliliters of added base. That equivalence point might have different pHs for each one of those acids, but we can conclude that all of these acids must have the same starting concentration if they're all hitting their equivalence point. So I'll write EQ point at 50 milliliters. Okay, so now there's a special point that I'm going to highlight at the 25 milliliter mark. And let's see if I can draw a nice careful line and see if you notice anything. And I'm going to call this the half equivalence point. And it's the half equivalence point because the equivalence point was at 50 milliliters. So the half equivalence point is at 25 milliliters. So check this out. As we scroll up here, look at this. When the Ka is 10 to the negative 2, the pH was 2.0. And these are not made up numbers. This is like real example here. When the Ka is 10 to the minus 4, the pH is 4. When the Ka is 10 to the minus 6, the pH is 6. When the Ka is 10 to the minus 8, the pH is 8. And when the Ka is 10 to the minus 10, the pH is 10 at the half equivalence point. So what we conclude is going on here, so at half equivalence point, the pH is equaling the pKa, right? Because if I took the negative log of 10 to the minus 2, right, let's do that. We can say 1 times 10 to the minus 2, right? And if I take the log of that, let's see, log, it's making me, okay, 0.01 log. I don't know why my calculator's not working all of a sudden. In any event, right, you guys know by now, the negative log of 10 to the minus 2 equals 2.0. So we can conclude at that half equivalence point, the pH equals the pKa. So how is that possible? Well, if you recall, okay, when we have the log of 1, that equals 0. So at the special condition where the pH equals pKa, this must mean that this log is dropping out. In other words, the HA concentration equals the A minus concentration, right? That would make that equal to the log of 1, which would completely drop out. So how is that possible? Well, if we do just a very quick before and after calculation, we know that when we add strong base to a weak acid, it's a complete reaction. that makes A minus and H2O, okay? So suppose that I have 1 mole of this. Well, at the half equivalence point, I'm going to have exactly half of that amount. We know at the equivalence point, if I had 1 mole of HA, I'd have to have 1 mole of OH minus. But at the half equivalence point, I have 0.5 moles of OH minus. And then, of course, we can say 0 and 0 of those initially. And now when those react, right, this is a limiting reagent situation, we know all of the OH minus reacts. So that means the same amount of HA has to react, which means the same amount of A minus is created. We don't really care about the water. And now, after all that's said and done, we have 0.5 moles of HA left. We have 0 hydroxide left. And we have 0.5 moles of A minus left. And now, look at that. My HA and my A minus are equal. And are part of the same solution, so that means their volume is the same as well. And that's going to give me this scenario where A minus equals HA, and thus that log drops out. So this is a very special point in our titration curves that I want you to be familiar with. At the half equivalence point for a weak acid, the pH will always equal the pKa. And that's another really good diagnostic for determining perhaps an unknown acid. For example, maybe you don't even know what the acid is that you're trying to titrate, right? Well, if you hit that half equivalence point, which you would get from first hitting the equivalence point, then understanding that the half equivalence point is half that volume, then you could identify the acid by looking up what that pKa value must be. So pretty cool.